Hi everyone, welcome back to Math 256. This is Scott. Let's get started. So, I want to talk about two things today. First off, we are not going to actually really cover section 2.6, but I want to hint at least what is covered in it. So, 2.6, and this is just a brief overview. And the reason is, I just don't think it would be proper to go completely through this term without formally putting into the record a mention, at least, of the most popular and in some ways the best of the numerical approximation techniques. So, the most commonly used numerical approximation technique most commonly used numerical approximation technique for first order ordinary differential equations is the Runge-Kutta method, commonly abbreviated RK4 because it is also known as the fourth order Runge-Kutta method, which is based on Simpson's rule. For numerical integration. And as a reminder on that, in case you either haven't seen Simpson's rule or it's been a while, the way that works is that it approximates a function with little sections, with little quadratic sections, little parabolic sections. Which approximates a curve with quadratic sections. But anyway, that's basically what I just wanted to mention. We are not going to make a big deal about covering the exact details of that because it's rather cumbersome for a human being to do, and instead it's the kind of thing that is best tackled with technology. But any numerical differential equation solving technique that you will see behind the scenes on something like a TI-89 or most other advanced algebra systems will be based on this particular method, the Runge-Kutta method, which dates back to around the year 1900, and which in turn is based on Simpson's rule, which dates back to the 1600s. Actually, technically, Simpson's rule goes back even further than Simpson. It was first used by Kepler in some of his calculations that he did when he was first discovering his famous laws of planetary motion. But that's a matter for another day. I just wanted to give you this so that somewhere in your record it would be officially recorded at some point the actual best numerical solution technique that is available even though it's too hard for humans to really do. Yeah, it is something that you could easily read about in either your book or some other source. Anyway, so there's that. Now the actual topic of the day is section 3.1, where for the first time we move beyond just first order differential equations and start talking about second order linear differential equations. So second order linear ordinary differential equations. And in particular, what's linear about them here is they are linear in y, y prime, and y double prime. So it's linear. The linear here means it's linear in y double prime, y prime, and y. That's what is linear about these. Now we're going to start our investigation of these with a specific category of them, and that is homogeneous second order linear differential equations. So homogeneous second order linear ordinary differential equations. These are a very specific subcategory of these, and what's homogeneous about them is this. So the format is a of x times y double prime plus b of x times y prime plus c of x times just y is equal to 0. And this is what makes it homogeneous, the 0. So homogeneous. So let's see. So what makes it second order is the second derivative of y. What makes it linear is the fact that as far as y is concerned, you've just got essentially a coefficient of the y double prime, although that coefficient is a function of x, but it's not a function of y. You've got a coefficient in front of the y prime. Again, it's a function of x, but it's not a function of y. And then c of x, which is again just a function of x, not a function of y. Now that's what makes it linear, and what makes it an ordinary differential equation is the fact that the y's here, their derivatives, are assumed to be with respect to x. There is only one independent variable in play here, and that is written by default with an x. Now the reason why we're going to start with these, for one thing, is that they're a little bit simpler than the general case, but for another thing, the term homogeneous here may remind you of a similar term that was used for a certain category of systems of equations back in linear algebra, and there is actually a very similar principle at play here. Only now, what we're going to call it is the principle of superposition, and it's related to an important linear algebra fact. So the principle of superposition. So the setup of this is that we have y1 and y2 are any two solutions to a homogeneous linear second order, we'll say here, although technically it doesn't need to be second order, but since that's what we're talking about, we'll put that in we'll put that in the notes. Linear second order ODE. So if we have that, then any linear combination of y1 and y2, and to make it concrete, what I mean is you have any y which equals c1 times y1 plus c2 times y2, where the c1 and c2 are constants. Then any linear combination of y1 and y2, such as this, will also be a solution to that same differential equation. So in other words, what this means, i.e., the solutions to a homogeneous linear second order ordinary differential equation form a subspace of the vector space of functions. So this is exactly analogous to finding the space of solutions to a homogeneous system of linear equations. So as an example, if we have the second order homogeneous linear differential equation y double prime plus just y is equal to 0, then we have y1 which equals just sine x, and we have y2 which equals cosine x. Then any linear combination of these, if these truly are solutions to this, then any linear combination of these will be another solution. So in particular here, sure enough, if you take the second derivative of sine, you get cosine first, then negative sine, add that to the original, it'll cancel out, and over here, the same thing is true for cosine. So these are two solutions, so then any linear combination of them will also be a solution. Then any y which equals c1 sine x plus c2 cosine x will be a solution for any real numbers c1 and c2. So c1 and c2, any real numbers. Now, linear combinations of functions mean the same thing here as they did in when we were talking about vector spaces, linear combinations of vectors. And by a similar token, we can actually say something about what amounts to a basis for this subspace. So if we have two functions, no linear combination of which, I should say no non-trivial linear combination of which is identically zero, we call them linearly independent. So in other words, i.e., if y1 and y2 are linearly independent, then c1 y1 plus c2 y2 can be identically zero only if it's 0 times y1 plus 0 times 2. Only when c1 is the same as c2, which is equal to 0. So that's that. So this amounts to the same thing. So effectively, for two functions, this is the same as just saying that one of them is not a multiple of the other. For two functions, this is the same as saying that no constant multiple of one will produce the other. Okay. Now here is where I'm going with this. There's a theorem that builds on the idea, there's a theorem that builds on the idea that the solutions to a second order linear homogeneous ordinary differential equation form a subspace. And that's that the subspace in question has in fact dimension 2. And what that means is if y1 and y2 are any two linearly independent solutions to a homogeneous second order ordinary differential equation, then any other solution to the same differential equation will be A linear combination of y1 and y2. So in other words, y1 and y2 span the solutions, i.e. y1 and y2 span, in the language of linear algebra, the solution space. To that homogeneous, linear, second order, ordinary differential equation. See here, I forgot to say linear, so squeeze that word in. Doesn't matter what order you put on the adjectives here. So you can put, say, linear, homogeneous, second order, homogeneous, linear, second order. Wherever in your writing there was space for it, squeeze the word linear in there. So they span the solution space to that differential equation. So it needs to be linear, homogeneous, second order. Here it does have to be second order because otherwise the degree wouldn't be 2 like this, or the dimension wouldn't be 2. Span the solution space to that differential equation. In other words, what that means is they form a basis for the solutions. Thus, y1 and y2 form a basis for the space of solutions. And remember here what the word basis means. It refers to a set that on the one hand spans the given space and on the other hand is made up of linearly independent members. All right, now here's a specific category that we will undertake in solving these homogeneous, linear, for second order ordinary differential equations. So a specific category of homogeneous, linear, second order, ordinary differential equations. And these would be constant coefficients. So the form then would be something like a y double prime plus b y prime plus c equals 0. So it's homogeneous because of the 0. It's linear because the y double prime, y prime, oops, cy, and the y are each basically linear, and then the second order because the second derivative, and the independent variable here is x, and that's the variable with respect to which these derivatives are being taken. So that's what makes it ordinary. All right, so now if this is our format, then what we need, we want the solutions, that produce the correct combination of constant factors to cancel out when we take the higher derivatives. Now, what does that exactly mean? It's a little vague. Let's just peel the band-aid off, and I'll tell you what the basic format here is going to be. So the basic format will be of this general form: y equals e to the rx. And the reason for that is then that y prime will equal r e to the rx, that's just the chain rule, and y double prime will equal r squared e to the rx. And we can then replace the second order differential equation with a second order quadratic equation. So then the differential equation looks like r squared e to the rx a r squared e to the rx plus b r e to the rx plus c e to the rx equals 0, which we can then factor the e to the rx out of. In other words, we'll have a r squared plus br plus c times e to the rx equals 0, but since exponential functions are never 0, for real values anyway, what we can get is we can just basically divide both sides by that, and we'll get ar squared plus br plus c equals 0. So this is called the characteristic equation of the differential equation and the nature of its solutions will tell us the nature of the solutions to the original differential equation. So there are three possibilities. Possibility 1. Possibility 1. We can have two distinct real roots, r1 and r2. So we can solve this this equation right here and get two distinct real roots. And then the general solution will come from taking the following. So y1 can equal e to the r1x, y2 can equal e to the r2x, and so then y can be what you get when you take the linear combinations of those, and you'll have c1 e to the r1x plus c2 e to the r2x. Okay, so that's what happens if we have two distinct real roots. Now, that doesn't always happen with quadratic equations, and so let's investigate the other possibilities. So possibility 2, a single, repeated, real root r. And we'll call it r1. So repeated real root r1. So now, for reasons that we'll not cover at the moment, we'll cover it later when we see more things in this vein. The general solution will look like this. Y is equal to C1 e to the r1x plus C2x e to the r1x. So this is what we need to do in order to give ourselves a second piece in order to span the solution set. There was never any problem with having a single real root. There was never any problem with that actually being a solution. The problem was that it wasn't enough to span the entire solution set. The dimension of the space of solutions should be 2. We'll see why exactly this one works after we try an example. And then 3. This is the most nuanced case, and that is a case of complex roots, and we'll say that they are of the form z, which equals, and there'll always be a conjugate pair, a plus minus, actually I shouldn't use the letter a here. I'm going to use z equals alpha plus minus beta I. So z is the default generic letter for a complex number, the same way x is the generic default letter for a real number. And whenever we have complex solutions to a second order, to a quadratic equation like this, they'll come in a pair, a conjugate pair. Okay. Now here we've got to do a little bit of work in order to figure out how that's going to play out. And here's the way it's going to shake out. So one quick note on those complex solutions. This is sometimes called Euler's equation, although there are literally hundreds of equations that Euler discovered. So this is just one of millions of different facets of math that Euler left his imprint on. Oops, equation. Euler's equation. And the important thing about this is e to the I x is equal to. So e to the I x is equal to cosine x plus I sine x. So this is an equation that is true, and if you want to know the reasons why, then if you've taken 253, you can find out the reasons from looking at the infinite series for these and the fact that all of the powers of the infinite series terms for sine are odd will be the key to that. But the important thing for us is that it is true, which means that e to the beta I x, or I guess beta I x, is going to be cosine beta x plus I sine beta x, and then that means that e to the alpha plus beta I x, which is going to be the same as e to the alpha x plus beta I x, is going to be equal to e to the alpha x times cosine beta x plus I sine beta x, which in turn is going to give us the key to the approach that we're going to be taking for the complex numbers. And so the way we can represent the solutions here will be to just basically take on each of these two pieces individually and take them as the two pieces of the solution. So then we can say that y1 is equal to e to the alpha x cosine beta x. We can say that y2 is equal to e to the alpha x sine beta x. And then we can make the general solution equal to y, which equals e to the alpha x, or c1 e to the alpha x cosine beta x, plus c2 e to the alpha x sine beta x. Or in other words, if I pull out the common factor of e to the alpha x, I'd have e to the alpha x c1 cosine beta x plus c2 sine beta x. So that's the general solution in the case of complex solutions. Now let's actually try some examples of each of these cases. So examples of these would be something like this. Let's say I had y double prime plus 7y prime plus 10y equals 0. So there's a second order differential equation, and so I can cut to its characteristic equation with an a of 1, a b of 7, and a c of 10. That's going to give me just 1r squared plus 7r plus 10 equals 0, which is then going to give me the two factors, r plus 5, r plus 2 equals 0, which is going to give me r plus 5 equals 0, or r plus 2 equals 0, which gives me r equals negative 5, or r equals negative 2, which gives me as the two branches of the solution here, y1, which equals e to the negative 5x, and y2, which equals e to the negative 2x. And then that gives me a general solution, y equals some unknown constant c1, e to the negative 5x, plus c2, e to the negative 2x. Now, if I wanted a specific solution to a specific situation, in other words, I wanted to find the c1 and the c2, I would need initial conditions in order to accomplish that. And in fact, what I would need is two initial conditions. I would need to have two pieces of data, one that I could use to solve for the c1 and one that I could use to solve for the c2. But we'll discuss that in a second. Now, the second example. So this one was two distinct real solutions, and in fact it factored out, so they came out as distinct real, not only distinct real solutions, but distinct real rational solutions. So let's say we had instead something like this. Y double prime plus y prime, and then something like minus 3y equals 0. So now we've got an a of 1, a b of 1 again, and a c of negative 3, which gives me the characteristic equation of r squared plus r minus 3 equals 0. Now this one can't be factored, so I have to use the quadratic formula, and that's going to give me that r is equal to negative b plus minus the square root of b squared minus 4ac, so that's going to be plus 12, all divided by 2a, which is then going to be r1 is equal to negative 1 plus root 13, all divided by 2, and r2 is going to equal negative 1 minus root 13, all divided by 2, which is going to give you the two branches of the general solution that you get by taking that as r1, that as r2. So c1 e to the negative 1 plus root 13 over 2x plus c2 times e to the negative 1 minus root 13 divided by 2 all times x. So the same approach, even though it looks different, is employed whether we have two distinct real roots that are both rational, in other words, the characteristic equation could be factored, or both irrational, which is the case when it couldn't have been factored. Now let's look at the repeated root situation. So an example of something like that might be something along these lines. Y double prime plus 2y prime plus y equals 0. So for our characteristic equation here, we're going to get r squared plus 2r plus 1 equals 0. So this is, again, just reading off the coefficients and changing the derivatives to powers of r, because each derivative you take of e to the rx is going to bring down an extra factor of r. So second derivative would mean a second power of r. First derivative would mean a first power of r. Zeroth derivative would mean zeroth power of r. So it's going to be r plus 1 squared equals 0, which means that r is going to equal negative 1 with multiplicity of 2. So it's a repeated root, multiplicity 2. So what that means then is that the general solution is going to be of that special form. So we're going to have a mystery c1 e to the negative 1 times x, or just negative x, plus c2. Now here's where it's special. There's an extra factor of x in front, and then it's going to be e to the negative x. Now to check this part, this part may seem a little strange to you. So let's just check the y2 equals x e to the negative x part. So this is the part that's novel about this. And if we were to check this, let's figure out the derivatives that would be in play with y2. So y2 equals x e to the negative x. y2 prime would be the first derivative of this, so we'd use the product rule. So it's going to be, so the derivative of the first thing is just going to be 1 e to the negative x. And then plus, the first one will be left alone, the second one will be the derivative, so that'll be a negative coming down. And now, if we want to take the derivative again we're going to get negative e to the negative x. And then right here, we're just going to get actually another copy of the same thing we just got, but opposite. And so that's going to be minus e to the minus x e to the minus x. So that's going to be negative e to the x and negative e to the x and blah, blah, blah. And we're going to get x e to the negative x. Okay. So oh, sorry, that's foolishness, just getting a little tired. What I mean is minus 2 e to the minus x plus x e to the minus x. There you go, that's better. I thought that seemed a little fishy for a second there, and right I was, that I was wrong. Okay, so now checking this, we should, if we put this into there, and this into there, and this into there, we should get what we were supposed to end up equaling, which was 0. So negative 2 e to the negative x plus x e to the negative x plus 2 times e to the negative x minus x e to the negative x plus x e to the negative x. So this is y2 double prime. This is y2 prime. And this is just y2. And the question is, does this really equal 0? So this is the commentary check. So the question is, if I were to perform all the algebra as necessary, will I get what I need to get? So negative 2 e to the negative x plus x e to the negative x plus 2 e to the negative x minus 2x e to the negative x plus x e to the negative x. Does that truly equal the 0 that it's supposed to be? And here, that cancels that, and these all cancel each other, and so indeed 0 does equal 0, and it checks. So this was all just because we'd never seen one of these yet, and we wanted to make sure that this second branch, the second term here, actually did make sense. Now let's see one more case, one with some complex solutions, complex roots to the characteristic equation. And so that'll be D, and let's go with something like y double prime minus 2y prime plus 2y equals 0. So here, the characteristic equation is going to be r squared minus 2r plus 2 equals 0. Now, this is not going to be solvable by factoring. It's going to require the quadratic formula. So here we had a equals 1, b equals negative 2, and c equals 2. And so then that's going to give us r equals minus b is going to be positive 2 plus minus square root b squared, which is going to be 4 minus 4 times a times c, which is in other words going to be 8, divided by 2a. So that's going to be 2 plus or minus the square root of -4 all divided by 2, which is 2 plus or minus the square, sorry, not square root, I'm just going to 2i divided by 2. Divide everything top and bottom by 2, you're going to have 1 plus or minus 1i. So in other words, according to the framework we've said, alpha should be 1, beta should be 1. And so then the solutions, the general solutions, are going to be y1 equals e to the alpha x, which is, so e to the x times c1 cosine beta x, and then plus c2 sine beta x. So that's what produced that, and this produced the coefficients inside there. Now to find the values of C1 and C2 in any of these cases, we need some initial conditions, but now because we have two pieces of information we need to have two pieces of information to solve it. So that requires two initial conditions. So note, initial value problems require two initial conditions for second order. For second order differential equations. Typically, we would have values for y of x naught, which equals y naught, and y prime of x1 equals y1 prime. Here what I just mean are, or we could also write this, y of a equals b naught, and y prime of a equals b1 would be another way of writing this. Something like that. And that'll give us a system of two equations to solve for the two unknowns that are the two c's. Now let's try an example of an initial value problem. So we'll have a second order linear homogeneous differential equation with constant coefficients, such as one we've already seen, y double prime plus 7y prime plus 10y equals 0, but now we will throw in a couple of initial conditions. Y of 0 is equal to 1, and let's say y prime of 0 also equals 1. So they don't have to be the same, but they also might be the same. You never know. Now from above, this was part A of the previous example. We already know what the general format of the general form of the solutions here is going to be C1 e to the negative 5x plus C2 e to the negative 2x. And so it's just going to be a question of what the C1 and C2 are going to end up being. Now, in order to evaluate this, we need to also figure out what y prime is going to be, so that way we can plug something into that equation as well. So it's going to be negative 5 C1 e to the negative 5x plus negative 2 C2 e to the negative 2x. So that means that if I plug in a y of 0 equals 1 initial condition into the first equation here, I'm going to get a C1 plus C2 equals 1. And if I plug in y prime of 0 equals 1 initial condition, I'm going to get negative 5 C1 minus 2 C2 equals 1. Alright, and now to solve this system of two linear equations and two unknowns, you can use any of the methods that you know and love. You can use linear algebra-based methods, you can use just regular algebra-based methods. I'm going to go ahead and do this with substitution method. So that'll be something like you solve one of the equations for one of the variables, and then you can plug that in for that variable in the other equation. So it's going to make negative 5 C1 minus 2 times what we just found, C2 equals, which is 1 minus C1 equals 1. Then do the algebra. So negative 5 C1 minus 2 plus 2 C1 equals 1. And then combine like terms, add that over there. We're going to get negative 3 C1 is equal to 3, which means C1 is equal to negative 1, which means then if we were to plug this value back in over here, sorry, my pen's running out of ink. I'll get C2 is equal to, better switch out. Emergency change of pens. So C2 is equal to 1 minus negative 1, which is in other words 2. So C1 equals negative 1, C2 equals 2 would be our conclusion here. And a quick check on that, will that satisfy the equation? Negative 1 plus 2 equals 1, yep. Negative 1 times negative 5 is positive 5. Minus 4 equals 1, yep, check. So it checks out. Which means that then the solution to the initial value problem is y equals negative e to the negative 5x plus 2 e to the negative 2x. Now, will this always work? It will always work if we have the correct format and if we have linearly independent solutions. And now the last thing that we're going to do is we're going to put down into the record officially another existence and uniqueness theorem. This is for second order linear initial value problems. So this is a theorem. And it is a second order, it has to do with second order initial value problems, and it's an existence and uniqueness theorem. So it's going to tell you some conditions where you can guarantee that a solution exists and that it is unique. For IVPs, for initial value problems under these circumstances. So here's the setup. What we have is a specific point. So a point, or a value. We have a value x equals a. I is an open interval containing a. So open interval means the two ends are bounded by strict inequalities, not less than or equal to, just straight up less than. And so we have a value that, we have that, and we have a diffie-q of this form. It's not homogeneous necessarily, but it is linear, and it's second order. So diffie-q y double prime plus p of x times y prime plus q of x times y is equal to f of x, where p, q, and f are all continuous on the interval I. And then for each b0 and b1, there is a unique solution y of x on the whole interval I, such that y of a equals b0 and y prime of a is equal to b1. So this is true not only for homogeneous differential equation, second order differential equations, but all linear second order differential equations where the functions that are the coefficients of the y prime and the y are assumed to be linear. Are assumed to be continuous. So there's that. And that concludes section 3.1, as well as our brief glance at section 2.6. Join me for the next episode of Math 256. Until then, bye.